Well, thanks for everyone for joining us today. So in this session, we're going to be discussing the basics of dust collection design for schools. All right, there we go. My slides didn't want to move on me today. My name is Amy Miller. I'm a training manager here at Donaldson Company. The purpose of today's webinar is to review the objectives of dust collection system design as it pertains to school woodworking or welding programs. We can help with other applications as well, such as paint booths, but wood shops and weld programs tend to be the most typical for schools. We're going to discuss the 4 primary components for a system design, including some common mistakes that we see. And then we're going to finish up with what's most people's favorite part, that Q&A session at the end. In case anyone on the call today isn't familiar with Donaldson Company, we've been solving complex customers' filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the world's first filter for a tractor engine. Today, we're one of the largest providers of unique filtration technologies, and we excel in providing high-quality filters and equipment. We have a global reach with a local touch, and our world headquarters is in Bloomington, Minnesota. We have 54 manufacturing plants and 23 distribution centers around the world. Before I introduce our guest speakers, I want to quickly explain how to engage with us in case for those of you that are new to our webinars and not familiar with WebEx. As you think of questions throughout the webinar, please type them into the chat box and we'll answer them towards the end of our session. And then during the webinar, the guys might ask you a few questions. You can respond with a reaction emoji. You can access these by clicking on the face icon at the bottom of the screen. And I think a few times they're going to ask you to chat something in as well. So just a heads up. And I'm pleased to introduce our featured speakers today. We have Dave DeCono and Chris Perot. We'll start with Dave. He's a senior territory manager with our industrial air filtration business unit. He's located in Watertown, Wisconsin. Dave's been with Donaldson for 31 years, covering central and northern Wisconsin and the upper peninsula of Michigan, serving customers with system design and problem solving in the dust collection industry. He has a background in fire service. He's a captain for a volunteer fire department for the last 16 years, and he's also on the Dodge County hazmat team. He has a bachelor's degree from the University of Wisconsin-Platteville in industrial technology.
Oh.
Thank you, Dave. We can see you, we can hear you. That's good. And then Chris is an industry segment leader at Donaldson for with more than 30 years of experience applying deep understanding of metallurgical and manufacturing processes to industrial filtration system design. His work spans a wide range of industries with a more recent focus on welding applications. So he's going to be handling a lot of the welding stuff today. He holds a bachelor's degree from Rockhurst University and an MBA from the University of Missouri and is a Lean Six Sigma Green Belt.
Hey, everybody.
And with that, Chris, I'm going to go over and hand it over to you.
Thank you. We would like to start by asking about your all's experience designing dust collection systems. So please select the reaction emoji that best aligns with your experience level. Okay, a little experience. We got an expert. Somebody's got a project coming up. Hey, we got a lot of good stuff going on here. And somebody looks like they're just happy to be here. We're happy to have you. That's great.
Awesome.
Okay. So let's talk a little bit about weld fume and wood dust generated at schools. There are a lot of important reasons to control the dust and fume generated in a weld and wood shop, such as improving air quality for the students and the staff, exposure control to reduce potential dust in the breathing zones for the students in the operating process, environmental concerns, EPA standards for outdoor exhausted environmental air quality and outlet emission requirements, safety concern hazards, NFPA guidelines for fire and explosion mitigation, cleanliness, concern about overall cleanliness of the woodworking and weld facilities. We got to set a good example for our students. Welding is typically going to be either a manual welding process like the weld cell pictured on the left, or a robotic process on the right. There are many welding processes, but the key point is this. Every welding process produces fume. Whether it's TIG, MIG, stick, or flux core, The differences are mainly in how arc is created and how shielding is provided, not whether fumes exist. Some processes create less visible smoke, others create more, but visibility does not equal safety. From a health and facility design standpoint, the takeaway is simple. If there is an arc, there is fume, and it needs to be controlled at the source. Welding fume particles are extremely small, small enough to pass your body's natural defenses and lodge deep in the lungs. Because of that, there's no safe welding fume. Every arc, every process, every day creates hazardous exposure. All welding fumes are classified as group 1 carcinogens, meaning they are known to cause cancer, not suspected, not theoretical. The risk doesn't stop at the lungs. Long-term exposure is linked to neurological damage, heart disease, kidney disease, and blood disorders. That's why welding fume is regulated and why it must always be respected, even when you can't see it. Welding fume is not one substance. It's a changing chemical mixture. The base metal contributes some hazards, the consumables add others, and the arc itself creates toxic gases. Surface coatings and solvents can make fumes dramatically more dangerous. Because the mix constantly changes, welding fume must always be controlled at the source. In school woodworking shops, not all dust is the same. At Donaldson, we group wood dust into 3 classes based on particle size and how that dust affects the type and size of filtration equipment needed. Class 1 is very fine dust, like what's created during sanding. Class 2 is medium-sized dust, typically from saws, routers, and joiners. Class 3 is larger shavings and chips produced by equipment like planers, edge banders, and lathes, which is what you're seeing in the video. The takeaway is that different dust behaves differently, and effective dust collection has to be designed around that. Combustible dust is another key risk in wood and weld shops. When combustible dust meets air and an ignition source, it can cause a fire. If that dust is dispersed, it can create a flash fire. If it's contained, it's inside a dust collector, it can lead to an explosion. We'll revisit this later, but for now, the takeaway is simple. If the dust is combustible, a mitigation plan is required to protect people and property. Let's talk about the basics of dust collection systems for both wood and weld shops. This is a diagram of how a source collection dust collection system works. A blower or fan creates an airflow, which is used to capture dirty air with a hood and then convey the material through a series of ducts to a dust collector. Here, the contaminant is separated out and clean air passes through the filter media to the fan, where it's discharged to the atmosphere and returned back into the building. Within these systems, every component is sized to the dust or fume characteristic, required airflow, and application needs. If one component is poorly designed, the entire system suffers. First, the hood is designed to determine the correct air volume, or CFM. Once we know the air volume, we can design the properly sized ductwork with the correct conveying velocity. We'll explain what that means in just a bit. And this is a spark trap. Third, we can now select the correct style of collector determined by the type and amount of dust, such as the cartridge collector we choose for this particular system. And lastly, we can choose the fan. We now know the total air volume, and we can calculate the total resistance or static loss, another term we'll talk about a little bit more later today, of our engineered system. As stated before, if one component is poorly designed, the whole system is affected. When we design collection systems, there's a lot more involved than most people realize. Things like the material being collected, airflow, pressure losses, and even future expansion. The publication shown here is the ACGIH Industrial Ventilation Guide. It's published by a nonprofit scientific organization and is widely considered the industry standard for proper ventilation design, including by OSHA. ACGIH also offers system design courses based on this guide, and members of the Donaldson Technical Engineering team have served as instructors in those courses. If you want to go deeper into ventilation and system design, it's an excellent resource. There are a lot of different formulas that we use in system design. The most basic and widely applied being airflow, the formula is Q equals V times A. The Q is the volume of air flowing through the system, often referred to as CFM, cubic foot per minute. To get to the airflow, we multiply the velocity of the air, which is the measure of linear speed for an object, by the area of the hood or duct that the air is flowing through. This formula is one of the basic building blocks of dust collection system design. We start at the pickup point and calculate using this formula to get to the needed airflow of each pickup. This will then give us the total CFM needed for the system. This formula also is used when calculating the needed velocity when the ductwork, what you need through the ductwork. Though the design of the system we refer to as Q equals V times A over and over. Just a few more terms here. Static pressure is the resistance to airflow in a system from components such as the collector, the filters in the collector, which will create more resistance when they are dirty, the hoods and the ducts. It's expressed in inches of water gauge or water column. And dust loading refers to the rate at which the dust will be entering the collector. Is it a little or is it a lot? Schools will generally experience low, medium dust loading in both wood and weld shops. So I'm going to pass this over to Dave, who's going to talk a little bit about hood design.
Hey, thank you, Chris. Back to our system diagram. The first component that we'll be talking about, like Chris said, is the hood. This is a critical component of system design that will allow the containment and collection of all fugitive dust. A well-designed hood is going to minimize the amount of airflow that is required to effectively capture and control the contaminant when it is released. It appears designed with good ergonomic principles and matter. It should be compatible with the material flowing through the work area, and it should be designed to minimize maintenance, other activities that may disrupt the process. When it comes to assessing an existing system, a few common mistakes I see are the wrong style of hood is being used, the hood is not being located in an effective position, or you have inadequate airflow to the hood. A closed capture hood is generally the most effective method of capturing material. The four most common types of capture hoods in order of increasing effectiveness but increasing fabrication cost are the raw edge on the left there, the flanged, tapered, and bell mouth hoods. I'd like you to use the chat box to let me know the most common types of capturing hoods that you've specified for dust collection. Any particular hoods that you guys have used in the past? Yep, tapered. I see that. Tapered. Good. A lot of variations of different hoods that have been used out in the industry. So we'll be getting into more details with that as we move on here. Okay, for weld fume, you see there may be large hoods like this, often with curtains for welding stations. We do a lot of testing at Donaldson, so we thought it would be fun to show you a few testing videos of our fume hoods. The video in the middle, which you can see there is moving, is using a smoke machine with the hood is being tested in the lab. This would simulate robotic welding. You can see that on the left. The video on the right is a more realistic for manual welding, where small amounts of fumes are being emitted and cleared. Extraction arms with a bell mouth hood on the end is another good solution for small weld applications, like those found in schools. They come in various lengths and diameters. The picture on the right was taken prior to the curtains being installed, but each extraction arm is where a different weld station would be located. And regardless of the style of hood, to be effective, a hood must be positioned properly relative to the point of contaminate is emitted. Remember, the first objective of a hood design is to minimize the air volume required to maintain capture efficiency. To minimize air volume, the hood must be close to the capture point without disrupting the process. Hoods simply can't reach out to control contaminant far away from the inlet. Let's say consider a vacuum in your home. To pick up the debris from the surface, the vacuum head must be close to the contaminant or it will have no effect. Hood positioning twice the distance from the containment emissions point rather than the capture point will need to draw approximately 4 times the amount of air to produce the same capture efficiency. Very critical to keep that close. And more air means larger collection equipment, larger ducts and larger fans with higher horsepower, all of which adds to capital and operational costs. When determining the airflow of a hood, the main design factor is called capture velocity. This is the velocity required at the point where the contaminant is generated in order to gain control of the contaminant and direct it into the hood. For school wood shops, capture velocity is typically around 300 feet per minute for wood, although it depends on the application and style of the hood. For school weld shops, it is generally between 100 to 250 feet per minute. 100 to 250 feet per minute. When you are designing hoods, you want to avoid airflow extremes. Too much airflow at the hood or pickup point means you're picking up good product rather than just nuisance dust. It could also increase the risk of capturing unwanted particulate like sparks and embers. And since more energy is required to move more airflow, it could lead to higher than expected operational costs. Now, insufficient airflow at the hood requires additional housekeeping measures to be implemented and, depending on the dust, may lead to an increased risk of student exposure to weld fume or wood dust. Once we design the proper hood to capture the contaminant, the goal is to move the particulate to the filtration system through the series of ducts. A properly designed duct system should pull the minimum airflow required at each hood and maintain velocities required to transport material through the duct and to the collector. And you have to be able to do this utilizing the least amount of energy as possible and minimizing any wear and tear on the duct components. Again, a few common mistakes that we see when it comes to dust design is the incorrect type of ducting is being used, the incorrect duct size or fitting is being used, and the dust system is not balanced correctly. The minimum duct velocity is a critical design factor. It is the lowest velocity where all contaminant will be transported through the duct system. If you go below this velocity, the dust could settle out within the duct and cause other issues. For school wood shops, this is typically between 4,000 and 4,500 feet per minute. Now for welding, Industrial Innovation Manual has a minimum of 2,000 to 2,500 feet per minute. However, we prefer to improve upon that and commonly use 3,000 to 4,000 feet per minute so we can keep conveying at a higher velocity and save installation costs with smaller ductwork. If the duct velocity is too low, dust could settle out within the duct and cause problems, such as safety issues. Now, let's imagine the dust collecting in the ductwork, like in the image, getting too heavy, and the ductwork falls and can ultimately lead to a total system failure and hurt individuals. If the duct velocity is too high, it won't create any safety concerns, but it will require more energy to move the air through the duct. Ultimately, this could cause impact of the size of the fan as well and create issues such as increased noise, abrasion, or wear and tear. So again, a critical design factor. Just a few pieces of advice when it comes to duct types. Rectangular duct is commonly used in HVAC applications where you're moving air only, but we don't want to use it in industrial applications because it could allow dust to settle out in the corners. Rectangular duct can be used on the clean air side as long as the duct vibration is mitigated. When specifying industrial duct, we sure to want to call out round, heavy duct, industrial ductwork. Most dust collection applications will use class 2, 3, and 4, as Chris stated, which are designed to SMACNA, SMACNA standards, which is the Sheet Metals and Air Conditioning Contractors National Association. Now, spiral duct can leak as a system is not sealed properly, so be careful, specifically spiral, when moisture is present. And be aware that flexible duct requires significant more energy than traditional hard ducting, so we recommend minimizing it as much as possible. Lastly, you want to avoid T's and 90-degree angles in your ductwork. As shown here, elbows, pictured on the left, should be a 2 to 2.5 to 1 diameter to centerline radius, except where spaces don't permit, in which case we can go down to 1.5 diameter centerline radius is acceptable. But if the elbows are mitered 90-degree turns, all the air must slow down, turn, and then speed back up. This creates a ton of turbulence, which adds more energy consumption and higher static pressure to the system. The same thing goes for branch entry, showed on the right there. Pictured on the right, you can see that 30-degree angles is preferred. So consider an elbow, a 1.5 to 1 radius to diameter, has a 0.2 velocity pressure loss. A 2 to 1, a bigger sweeping elbow, has 0.19, and a 2.5 to 1 has 0.17. The lower that value of velocity pressure loss, the less static pressure you need in your system. And now the 90-degree branch entries, a 30-degree is 0.18 inches of loss, a 45 is 0.28, and of course a 90 in the elbow is a 1 velocity pressure loss. This was added up to determine the total static pressure required in the system when selecting your fan. As I mentioned earlier, having an unbalanced system is something that can go wrong with duct design. When customers add new equipment to an existing system, they often don't consider the impact it has on other existing equipment. In most cases, existing equipment wasn't modified to accommodate the additional airflow or static unless it becomes unbalanced. Luckily, if you know a school is going to be expanding their process, there are ways to design future lines into the system so they don't have a sacrifice performance. Now I'm going to hand it back to Chris to talk about dust collection.
Thanks for the explanation on the ducts. Hey, that was wonderful. The main objective of a dust collector is to deliver sufficient efficiency while operating in a predictable, stable, and economic fashion. The most common mistakes are things that could go wrong that we see when it comes to the dust collector designs are wrong filtration technology, incorrectly sizing a collector, either too aggressive or too conservative. Aggressive means too small, conservative means oversized, or poor installation, inlet orientation, and outlet fan locations create airflow and dust distribution problems within the collector. When it comes to school weld shops, you're going to be specifying a cartridge collector, either a standard collector or a specialized one, such as the ambient collector in the middle, or that portable unit on the right. Cartridge collectors were introduced by Donaldson in the 1970s, have come a long way since then. A high percentage of collectors sold in the marketplace today are cartridge collectors due to their small size and lower initial cost. And compared to a traditional bag house, the filters are much faster and easier to change out. They are best for low to medium grain loading, as well as fine, uniform, dry dust types, like what is generated during welding applications. In most school weld shops, the system is built around one cartridge collector serving multiple weld booths. At each booth, fume is typically captured using either an artificial extraction arm or a larger capture hood. A common example of this setup is a downflow evolution cartridge collector, which is most often installed outdoors, though indoor installation is also possible. For schools, airflow is usually in the 2000 to 7000 CFM range. This type of collector is typically the starting point for a system design, and if it doesn't meet the application needs, other options can be considered. So here's another cartridge collector example. This is Workshop for Warriors, a not-for-profit weld school that trains veterans in the welding field. On the left, you see a humble student's weld cell with just a snorkel hood. Then in the middle, you see a nice manifold with multiple pickup points going to each one of these little student cells. That's probably 10 on one side, 10 on the other. And then Donaldson donated one of our vintage DFO cartridge collectors to the school. I'm told they capture 3 barrels of dust every 9 semesters, and they're able to sell it to the recyclers. So, interesting operation, but that's kind of what a manual weld school looks like. If school only does occasional welding and needs an inexpensive portable solution, you may consider specifying portable fume collectors like the Easy Trunk. It can be easily moved around and doesn't require any kind of ducting. It's a pretty handy little collector for welding. Weld.com, it's an industry influencer. They made a video recently and they used the Easy Trunk. Let's play a little clip from that, if we could, please.
Until we get it right. Until we get it right. Until we get it right. Until we get it right.
Very good. Okay, so in most cases, source capture is a preferred way to control welding fumes. When equipment, layout, or obstructions make source capture impractical, ambient fume control can be an alternative. Ambient systems work by filtering air as weld fumes naturally rise toward the ceiling, reducing the overall fume concentration in the space through regular air exchanges. Ambient control is often used where ductwork or hoods aren't feasible or where weld stations need to be easily moved or reconfigured. The system shown here is a tower style ambient collector with a small footprint, and facilities often use multiple units arranged through the space for effective coverage. In terms of cartridge filter media, it's important that you select the best option for the specific applications. There are a few we see the most often in schools, typically UltraWeb or UltraWeb flame retardant, but it's important that we understand the specific process so that we can make the best recommendation for you to specify. Um, like oily fume and things like that, those are considerations that you should consult Donaldson with, because there's all kinds of ways to mitigate these types of problems with the media itself. So Dave, you want to talk a little bit about the wood shops?
Yes, thank you, Chris. When it comes to school wood shops, the most common will be the small bag house, a cyclone collector, or a standard cartridge collector, as shown in the picture. We aren't limited to just these. This is just what we tend to see in schools the most often. Sometimes you run across oddball stuff. We have over 30 different collectors, so wide varieties to choose from based on your customer's needs. Many schools specify small bag houses, such as the Unimaster shown. You may want to consider a small bag house when the school is looking for the following: a small self-contained collector. It's packaged with the fan and fan motor, an automatic shaker and shaker motor, and system controls. instead of using plant compressed air like a DFE does. It has a mechanical shaker that essentially shakes the dust off the filter. This type of collector is best for low grain loading applications, which is pretty typical for schools. Intermittent duty means it must turn off to clean, which usually works well in school wood shops, since there will be more downtime than you'll find in woodworking factories. It can handle airflows up to 8,000 CFM, depending on the static pressure required. The higher the static, the lower airflow can be accommodated. The larger built-in fans, which is up to 30 horsepower for practical bag houses. It can be set up as a centralized system, like multiple stations or machines, or a single machine. I most commonly see standard 8-ounce polyester filters. As you can see from the picture at the right, this is a one-piece design, and it sits on a metal frame, and each of the metal frame meshes an insert. Depending on the application, you may need to consider an anti-static bag, and there are many other options too if needed. Moving on to the next collector, the Cyclone collector is a little different, is that it uses centrifugal force to remove dust particulate from the air. It can handle larger dust particulate, like class 3 dust, and high volumes of dust. It just can't handle the small dust. Like it would work for weld fume. It wouldn't work for weld fume, and it wouldn't work for a lot of fine sanding dust because the particulate is too small. The third item we're going to present here is the Downflow Evolution, the DFE cartridge collector again. It's the only one that can really handle either weld fume or wood dust. But with the same system, you can mix the fume and the wood dust together. I tend to recommend this for schools when they combine the processes together. The one picture shown here is a DFE 2-8 at a school, handling about 4,500 CFM at school in Wisconsin. As you can see, it has dual 55-gallon drums underneath it with an airlock to isolate for an explosion, and explosion isolation devices installed on the ductwork. As you can see, those red devices there, which we'll get into in a little bit. Here's an example of how I use the DFE collector for weld fume shop, and a Cyclone collector for a wood shop. As you can see there, sitting side by side. Basically, this was another high school in Wisconsin, Seymour, which you may know of. They love the operation of the two systems because they have the Cyclone with a spark cooler in it, so we can minimize any sparks or any fires in there. And basically on the cartridge collector, so they can actually put a mitigation equipment, as you can see on there, those red devices there, and protect the operators and people and students inside the building for a combustible dust issue. Now, when I'm designing a system, the very last thing that I do after completing all of the airflow calculations is select and size the fan. The fan is the heart and soul of the exhaust ventilation system. It has two job responsibilities. First, the fan must deliver the necessary volumetric flow at the required static pressure to drive operation of the system. And since many dust collectors can operate with clean or dirty filters, the required airflow often has to be maintained over a range of static pressures. And secondly, the fan you select must be able to deliver the desired static and airflow with the appropriate energy efficiency and acceptable sound levels. For example, non-material handling fans located on the clean air side of the collector are more efficient than material handling fans on the dirty air side of the collector. Fan challenges generally fall into two categories: poor fan selection and or poor installation. And a critical component to the fan design is static pressure, which again is resistance that the airflow must overcome due to the system components. It's expressed in inches of water gauge or water column. When we design a system, we calculate the total system static pressure so that we can size the fan properly. Here's an example of the items that we're adding up individually. The hood totals 1.5 inches of water gauge. The ductwork, including straight runs of duct, elbows, and branch entries, totaled 2.5 inches of water gauge. And the filter on the collector totals 6 inch. there's a dirty collector filter, 6 inches water gauge. And the filter of the fan ducting was a 1-inch water gauge loss. And the spark cooler that we had on this is a 1-inch loss. So when you add all them, total system static pressure for this particular project is 12 inches of water gauge. Okay, so fans are sized based on system's total static pressure and the required airflow. For example, let's say that I need to size a fan for this example, like I gave you earlier, 12 inches of water gauge and an airflow of 9,000 CFM. We use a system static pressure of 12 inch, as you can see there, and line it up with the airflow 9,000 CFM. And when those lines meet to factor up, we land between the backward inclined fan TBI 25 horse and a TBI 30 horsepower. So we go to the curve to the right where we land, since we rarely land on the curve. And in this case, I would select a TBI 30. You can always have more airflow, but if you don't have enough, you can't make up more airflow. See how the static pressure is so important? A required airflow of 9,000 CFM achieved with 3 different fan sizes. It could fit into a TBI 20, TBI 25, or a TBI 30, depending on the amount of static pressure that you need required on the system. Okay, to finish things up, and then I'll open up for questions. There are a few other design considerations to think about. The first one is the total cost of ownership for the school's dust collection system. This is critical. An example, how much energy is required to operate it? Where is the unit coming from? Shipping. How easily is it to get parts, replacement parts? How long do the filters last? How is it sized? How easy is it to change filters out to maintain the system? And what is the life expectancy of the system? Many dust collector manufacturers are now offering the ability for operators to monitor the system remotely. At Donaldson, we call our system IQ, which essentially makes a dust collector smart. This allows a school to be able to monitor their dust collectors remotely. It provides them with real-time data, alerts them when there is an issue, and provides historical data, historical reports. As you can imagine, customers find this incredibly beneficial. Again, most manufacturers are heading in this direction, and customers love it. It's definitely something to consider when specifying a system. And moving on, and regulatory considerations are everyone's favorites. As you can see, the entities that are up there. Each of these agencies may have different expectations to reduce process-related hazards, and as we know, they aren't always consistent with each other. Knowing the hazard related to the process the system is designed to handle will enable you and the school to make some of these critical design decisions up front in the process. It can be very expensive and time consuming to change the design once the equipment is installed and in operation. Okay, here's my fire part for you. I wanted to briefly come back to the topic of combustible dust. The National Fire Protection Agency, or NFPA, is a global self-funded nonprofit organization devoted to eliminating death, injury, and property and economic losses due to electrical and related hazards. NFPA. Standards developed by NFPA are called census standards because they are widely recognized by authorities. NFPA standards are referenced in the national, international fire and mechanical codes, which are adopted by many states and municipalities. And if so, local inspectors and fire marshals may be required to enforce NFPA standards. OSHA, also considered NFPA standards, is to be good engineering practices, and during a general safety inspection, may reference NFPA standards when issuing a fine to a facility under a general duty clause. The authority having jurisdiction, the AHJ, they will be the deciding authority. It could be the fire chief, insurance company, OSHA, NFPA, etc., whichever body is making the decisions. Your authority having jurisdiction has control over the process. Okay, getting into some of the mitigation examples. First one would be the inlet and outlet isolation. Dust collectors must be isolated from dust collection in the event that a deflagration in order to keep the event from spreading back into the process or the return area. This is done typically with a mechanical isolation valve, but chemical isolation systems are more prevalent in the battery manufacturing industry. Deflagration isolation, our DFE collector, was independently tested and the filter successfully isolated the deflagration and allowed no flame or spark to pass into the clean air plenum. This is an important consideration when returning air back into the facility. It may help you eliminate a high speed abort case. Hopper isolation, that's typically a rotary airlock or specific design drum to prevent explosion from propagating through the dust collection hopper outlet. And the other thing is explosion venting of outdoor units and chemical suppression for indoor to help minimize and eliminate damage to the dust collector, and flameless venting, which also can be discharged inside. So basically to make sure an explosion before it becomes catastrophic. Again, this is a complicated topic, and if you have any questions, reach out to your TM or your dealer. They can help you out. Back to Amy. It's up to you.
All right, great job, Dave and Chris. Thank you. Designing dust collection systems for schools can be complicated. There's a lot that goes into it, right? But that's what we're here for. We've sold countless dust collection systems around the world. We have local support in your market, and we are here to help you in any way that we can. We're going to finish up some Q&A. Dave and Chris, you can go ahead and turn your cameras back on now. Just a heads up that everyone who attended will receive an email that includes your professional development hour credit. If you don't get yours, send us an email. The email address is on the screen. That goes right to me. There's a few QR codes if you're interested up there as well, including the events page for live upcoming webinars and the on-demand page where we post recordings of past webinars in case you want to look at something again. A recording of this webinar will be available on the site as soon as possible. It usually takes us about a week. Also, in case anyone isn't aware, we do have a 5-hour in-person class on system design for engineers. It gets much more in depth that we can cover in this hour. We're holding them in different cities across the country, and coming up we have Chicago, Minneapolis, and Kansas City. So if you happen to live within a drivable distance or reasonable distance from any of those locations, shoot me an email to training@donaldson.com, and I'd love to get you some more information about that. All right, so I'm going to turn my video back on myself. There we go. Okay, so the first question, you guys, I did want to bring up, just in case, I want to make sure we address this before anyone drops off the call. So Dave had misspoke. It's okay, Dave. So someone had asked, I didn't think you were able to mix dust and weld fumes into a common duct because the potential for fires. So I think what Dave meant was that like some collectors could be used for both weld fume and wood dust, but they can never be mixed together in a common duct, right, Dave?
You normally don't want to put them together. Correct. Yes, that's correct.
Yeah.
I'm
Okay. So
sorry.
I think he meant to say they can't, and I think he said they can, and he just misspoke. So I just want to make sure that everyone caught that information correctly. It is what it is. It's okay. All right. So let's go back. I'm going to go back into the chat box, and look, we've got a bunch of questions in here, you guys. So that's awesome. So sorry, I'm getting through all the tapered hood things. Okay, here we go. Can you elaborate on moisture concerns with regards to spiral duct? Either one of you guys.
Chris, you want that one or you want me? Doesn't matter.
You could do that one, Dave.
Okay, I'll take it. Spiral duct, of course, as it's manufactured, is compressed when the seams are sealed around the duct. And it's a continuous seam around the duct as it goes through there. It's not positively sealed off. When you get some mist applications on mist collectors, we do not use them because they do leak. If you went through and sealed off the whole inside of that spiral duct with some type of adhesive or some type of sealant, you could use it. But as a whole, we don't want to use that on mist collection. On dust collection, it draws air into there. It's usually pretty good. But as your mist runs through the ductwork, it coalesces out in there and settles out in the ductwork spots, and it can drip through and create slip trip hazards in other parts of the facility.
All right, thank you. Here's our next question. In applications like steel plate cutting table, what can cause the increase of air temperature that reaches the collector and damages the filters over the years, assuming same work conditions?
I'd like to take this one, Dave. So if all conditions are the same, I could go out on a limb here and say maybe your filters are plugged. Maybe your magnehelic gauge is broken. And they didn't tell you that your filters have crept up in differential pressure, so you're not getting adequate evacuation if all things are constant. But things that aren't constant that can cause high temperature is maybe you've changed materials. Maybe the materials that you're cutting have lubricants or other hydrocarbons on them that create more heat. And then lastly, just because you have the same machine doesn't mean that it can't be upgraded. And who doesn't like more energy in the same machine? So maybe you got a way to put more watts into it or more gas into it to burn and cut more pieces faster. That could also lead to higher temp. Those are my 3 points there.
Thank you.
Sometimes,
And the
yeah,
next one we
sometimes the
already.
fan, actually, the motor does create heat too. A little bit of energy may go into the airstream, but that's only 1 or 2 degrees, not a critical amount, like you're thinking.
Thanks, guys. All right, so next question. If moisture is a concern in the ductwork, would you plan to go with stainless steel in lieu of galvanized?
I would just say flanged welded ductwork when it gets moisture in there, when there's stuff in the ductwork. If the oils or whatever's in that is compatible with galvanized or compatible with whatever it is, that's the material you want to use. So if it's got some aggressive tendencies to it, you may have to go stainless steel because it'll chew up galvanized or chew up other materials. So, but yeah, it's determinant on the type of oils that are in there of what you'd want to use for a material. But welded flange is your best, sealed off with O-rings on the flanged ends of it, so it's sealed off completely with mist.
Thank you. All right, so next question is about balancing a system. How do you balance a system? Are there dampers suitable for dust collection?
Go ahead, Chris.
Dave, I'm going to let you have that one.
Okay, I'll take this one. Okay, so balancing a system is pretty critical. Basically, you want to set up your system and have the maximum airflow. You want to set your system at your design airflow where it's at, say 9,000 CFM. Then each of the branches that are out there, you want to have a certain amount of dust, certain amount of airflow going to each of them to have your maintaining your velocity in them. So yes, blast gates are used on them. Sometimes butterfly dampers are used on them. I know that a lot of times NFPA has issues with blast gates because dust can fall on the back side of them, but if they're properly installed in the vertical orientation, that shouldn't happen. So yeah, blast gates are typically the way we do it, or making the diameter of the duct bigger or smaller to create the same amount of resistance on a drop that is consistent with it. So say you have a 6-inch drop, you have 900 CFM going through it. Now you have a 4-inch drop, you want 400 CFM through it. The diameter of the duct will actually restrict airflow a little bit. So you may make it a little bigger, a little larger to get that exact airflow and balance the whole system out. Now the critical thing we went through in the middle of that is if you're changing things around, all bets are off. You're adding stuff into a different line on the machine. You almost want to run a separate line out of the dust collector to handle the other process to maintain the constant airflow or maintaining velocity on the balance system, if that makes sense.
Thank you, Dave. All right, next question. Thoughts on quick fit duct systems for sawdust collection?
Quick fit. What do you mean by quick fit?
I don't know.
Easy duct, maybe?
Easy duct, quick fit. That could be
Maybe,
flange ductwork.
maybe.
Yeah.
I mean, that's flange ductwork too. That works fine. The rolled flange with O-rings in them. It's all sealed off. It's all welded. There's no spiral in it. That would be if it's a quick fit that way. I don't know if he meant a smaller plug and play unit, quick fit.
Whoever asked that, you can go ahead and chat in a follow-up question if we didn't answer your question properly. All right, so here's our next question. Do you have examples of connections to equipment for collection and not just a hood? Okay, so this is when you're ducting directly to a piece of equipment. I know CFM and duct sizes are often listed to those, but I was curious on Donaldson's recommendations.
I mean, I think the process and what you're creating the dust on, if it's a planer or joiner, that typical hood will cover the whole length of the process point where it's generating the dust, therefore requiring so much CFM to maintain that capture velocity of 300 feet per minute. So you have a hood that's a foot by a foot. that's 300 CFM that you want coming in there to maintain that 300 feet per minute velocity because it's 1 square foot. So if it's smaller, it's smaller. If it's larger, it's larger. You base it off of there. So tapered hoods are nice on dust collection instead of a straight roll flange. The straight edge is a 1 velocity pressure loss. The tapered duct actually drops down to a 0.6 or 0.5. So it'll actually help in your friction loss on your system also by using tapered or transition hoods instead of rolled edges. The bell housing is the most effective one because it's got a rolled edge on it and it's smooth when it comes into the ductwork.
Okay, so if you're gonna duct directly into a machine, I mean that's kind of the hood, right? You would recommend a flanged.
Yeah, I would
Yeah,
recommend a
check.
flange to it. Yeah,
Okay.
if it's an open machine, but if it's a closed machine, then you just connect to whatever connection it is. If it's 6 inch, 6 inch, you put that on
Right.
to the machine. But if it's a surface grinder with open area, you're going to want to have a hood that's going to be tapered to draw it off and make equal collection across wherever the dust is going into the ductwork.
All right. All right, next question. We kind of talked, well, I guess we didn't totally talk about it. How do you deal with blast gate isolation of unused equipment or floor sweeps and maintaining minimum duct velocity? So using blast gates, but you're closing them off for equipment that you're not using at the moment. How do you make sure you're getting the right airflow still?
Well, yeah, it's a tricky question to answer because every time you move a blast gate, you're going to have different airflow there. Normally, when you do floor sweeps, you shut off a bunch of different blast gates to get the velocity up in the floor sweep to be able to suck the dust up off the floor. But yeah, it's a hard way to explain it. I mean, you could put some type of barometric balancing damper in to bleed in air if you shut too many gates. But realistically, I think more airflow is never going to hurt you. Less airflow will not capture and won't convey it. So I guess I'd look at it that way. If you're shutting more blast gates, you're better off than have a higher velocity than a lower velocity where dust can settle out in the ductwork.
All right, thank
Hopefully that
you.
answers the question.
Options on overhead versus below slab ductwork for sawdust collection.
Overhead versus bottom. I mean, a lot of times your table saws, you're only going to be able to collect off the bottom. That's where the dust is going to go down in the cavity that's underneath the table saw, unless you have a shroud around the top of it that has dust collection on the top of the blade with an enclosed collection point there. So most of them, I think we like to use a side draft, normally off to the side versus top and down, that it draws the dust into that component of that hood and then conveys it to the dust collection. But either of them, well, actually, all of them work. It's just a matter of the top one will collect a little bit less than the bottom one because the bottom one would have it flowing down with gravity into the hood, where the top one would have to overcome gravity and suck it in. The dust would have to come up vertically instead of going down into the ductwork.
Thank you. So the next one, I feel like we kind of addressed it, but I'm going to ask it just in case you wanted to talk a little bit more about it. How do you design the manifold duct diameter when not all emission points are working at the same time? I'm considering you may experience low velocities if you're using dampers to close points that are not in use.
I think I kind of
I,
touched on that with the barometric damper. Chris, you got anything to add to that? Or do you want me to take that one?
in a very big weld school, let's say if you got, 40 different student weld booths and you only have 20 students, systems can be designed in zones. So it probably not practical, and I defer to your experience, Dave, but to, cut off each and every little weld cell where somebody's not at, but you do it in zones. So if you don't have a full class or a full room, you can just, cut it in 4 different zones and 10 people can weld, or turn it all for 40 people to weld. I've seen that in weld school design.
All right,
In
thank
welding,
you.
of course, in welding, it's a lot easier to handle at 2,000, 3,000 feet per minute. Now, when you get into wood dust, you got to be critical on where your compressor, where your manifold would be to make sure that you're maintaining a minimum amount of velocity in that manifold at 4,500 feet per minute or 4,000 feet per minute. So that's critical.
All right, thanks, guys. Next question. Does the exhaust fan for weld fume need to be rated for high temperature, like greater than 500 degrees Fahrenheit?
I have not seen a weld process that has been elevated to that temperature that I've operated with. even plasma cutting tables, laser cutting tables, manual welding, all that stuff. I can't see it getting above, ambient, which might get to 100, 125 or something, possibly 150, but I don't see it getting up more than that. But yeah, if the temperature of the airstream coming in for some reason it's got a lot of sparks and embers in it and it's creating a lot of heat, yes, you'd have to accommodate for the temperature on the fan. Yes, you would. But normally I don't see it in the industry as elevated temperatures on fans.
Yeah, a lot of dilution air goes into any, weld hood. It's not a sealed process typically. You're just capturing the smoke. The concern is a spark and some sort of hydrocarbon carryover from what's being welded, getting on the filters and causing a fire. So I'd say more fire mitigation, not necessarily exposure to 500F for a long period of time, or if any, it should be a somewhat near ambient temperature typically.
Yeah, our filters, our cartridge collector's only rated to 170 degrees. If you got 500 degrees in there, you're gonna filters.
If let me say this, if you think that you're going to have to operate a fan at 500 degrees for a weld process, call your territory manager at Donaldson to come in and have a chat.
Yes, I agree. Bleed in air. You're gonna have to bleed in air or go to bags.
All right. Would you typically specify a dust collector with a VFD?
I would say my school jobs in Wisconsin, 90 to 95% of them have VFDs on them now. The ones I've sold in the last 3 to 5 years, they all have VFDs because they want to maintain constant airflow. They want to have set up a system that's going to be rated at 5,000 CFM. It's going to maintain 5,000 CFM, so to ramp up and ramp down the VFD to do it. It's an added cost. There is a reward you get from Focus on Energy for VFDs, so you can get some money back. But I see most of them in my systems. Yes, VFDs are very prevalent in the school jobs that I've sold recently, for sure.
Chris, how about you? Same thing?
A VFD is a really nice thing to have if you got it in the budget, to have control over the flow and suction based on the demand of the need for evacuation. So if you can afford it, I think it's a good thing to get, and the controller.
All right. Next question. Does NFPA 660 require a dust hazard analysis? We've had them required. We've been seeing them more and more being required.
I think that's an AHJ question. Authority having jurisdiction, that's going to have to tell you if it's required or not. You do need to be able to produce a KST value, which is an expansion rate of the dust, which is what's achieved by the testing of the dust. But if there's stuff out on the internet that you can say this dust will not exceed a certain KST, then you can use that value. I guess I would say it's all dependent on the authority having jurisdiction. If they're going to require it for stability and security, that it's not going to have an issue. Really.
All right. So consult your AHJ just to make sure. What about the use of an explosion valve in a dust collection system?
Explosion valve, explosion vent, explosion valve.
It says
We use
explosion
venting in
valve.
our dust collectors quite regularly. It says valve, explosion valve. I'm not familiar with an explosion valve on dust collection. We have, airlocks on the bottom to isolate the combustible dust from going through that next going through there. But I don't know of an explosion valve out there that we have. We use inlet isolation valves, if that's what they mean, explosion isolation valves. That would be separate if there's an explosion in the dust collector to allow it to vent through either flameless venting or through the explosion vent externally from the building. That would be an explosion valve, isolation valve. We use them quite regularly. As you can see in the pictures that I had on my school projects, all those school jobs on wood dust. Wood dust is a combustible dust. It requires NFPA required inlet and outlet isolation on it. And that's what our engineering firms have specified, inlet and outlet isolation. And sometimes they do some type of chemical suppression if they need it, if it's on a metal dust or something.
Thank you. And if you do have specific questions about what, if you have questions about how different devices work, like mitigation devices work, reach out and let us know, and we'll help you through that. Next question. I don't see explosion isolation devices being installed between your collector and the blower. Are Donaldson blowers rated for isolate or deflagration pressures that could be experienced in a deflagration event?
I would say yes, and the ductwork between the fan and the collector are built to withstand that pressure also. Yes, because our fans are typically on the smaller airflows are mounted, direct mounted to the collector. So it's right onto the collector. The collector construction is to a certain KST value, and the fan is built to that similar KST value. So it shouldn't be a weak point in the system if there would be an explosion there. So yes, it would be.
It's an option though. It's case by case. Somebody could have one. No, Dave?
If it's remote and you got ductwork between the two, then you got to consider making sure that the fan is built to whatever KST values we need to have it protected. Because it would be part of the isolation. If the isolation device is after the fan, that fan would be under pressure and potentially could have a risk of failure there and be a failure point in the system. So yes.
All right, so we are at time. Do you guys have maybe 5 more minutes to answer the rest of the questions, Dave and Chris?
Sure.
I'm okay to go. Yep, I'm okay. Yep.
Okay. All right. So next question, what airflow should you use for sizing systems with table saws, planers, drill presses, belt drum sanders, etc.? So woodworking.
Woodworking, again, like I said in the presentation, is 4,000 to 4,500 feet per minute. If it's larger dust, larger chips and flakes and stuff that coming off like a router or something, they can take some pretty big chips. You may even go 5,000 feet per minute in the ductwork, possibly. Again, your territory manager can figure that out. Your dealer can figure that out for you if you have a real heavy industrial dust. But yeah, 4,000 to 4,500 for conveying, minimum. Higher doesn't hurt you.
All right, next question. When is it acceptable to use portable collectors?
Is it acceptable? Go ahead, Chris.
I'd say it's if you have a very small shop and you just need to weld some things occasionally, maybe you're not going to be welding every day, but you needed to do a little bit of welding at a time. You have the portable collector, you can bring it over and put it over your work, keep everybody safe, and then you can move it back over to the corner. If people are going to be welding every day, more permanent solution is required.
Yep. I would say be careful. Again, combustible dust is the main issue. You typically don't want to run a portable dust collector on a combustible dust because if you would have an explosion, it becomes a rocket. So you just think of it that way. Just think about you just don't want to do it.
All right, next question. Why use a dust collector for a welding hood? Where is that required?
So, the alternative to dust collection and weld fume is the open door. Okay, you just blow it on out. So that's understandable, but in this day and age, people are starting to understand the harmful effects of weld fume, not just to the worker, but to the community that surrounds it. So welding hoods, need to lead to dust collection to capture the weld fume, which can be harmful to humans. So I would just say that it is becoming more and more required to capture that weld fume, although it's not being captured everywhere.
Yeah, and I'll add a little bit to that. There is a maximum exposure limit over an 8-hour time weighted average. So if there's a dense concentration of fume in that area, that's going to be a consideration where it may be above OSHA standards. You can't utilize that, have them in the environment that long because it's a hazard. And of course, operators that are in these facilities are always looking to make more money. And if someone's building is cleaner than the last person's building and they're doing ventilation, they're going to probably move on to the cleaner building, So that's kind of two things that I've noticed out there. But yeah, there is some OSHA regulations for exposure to that contaminant. So dilution is the solution, as Chris said before. Getting it down to a lower level, dumping it outside if you do, so be it. But yeah, you want to keep the air clean. And it just costs so much money in the winter to heat that air. So you want to put ventilation or dust collection in or dust filtration in the winter months for sure.
Yeah, and you're in Wisconsin, Dave. So it's cold. You got to capture it. People down in warmer climates in Texas and Georgia, they're able to keep everything open and not worry about wasting heated and air conditioned air and things like that. So there's a regionality to it as well. So it's an interesting question. Thank you.
All right, just a couple more questions. You mentioned the downflow has been tested to be a sufficient means of explosion isolation. Can you provide the testing data and a list of qualifiers for that system? It's on the
Yes.
brochure, isn't it?
Yes, it's in our literature. Yeah, Amy, it's in our literature. If you go on the Donaldson, www.donaldson.com, find the industrial air filtration group and look under cartridge filtration, the DFE is in there. In our brochure is the testing that we've done on it and what it's supporting and what it does. We can also supply other documentation if you want it. Yeah, just reach out to your TM, your territorial manager. He has all that at his fingertips. He can supply that to you. Not a problem.
And if you don't have a contact, the person that asked that, shoot me an email to training@donaldson.com and we'll make sure and send you in the right direction and get you what you need. So thank you. All right, which do you recommend?
That's also on the
Is it?
website. If they go
Yeah.
to www.donaldson, they can go in there and say find a rep and boom, it'll punch up the TM.
Good point.
I would say this, the DFE brochure does show you an exploding DFE, and that explosion goes straight up by design to not have to consider deflagration zones and things on the perimeter of it. So it was designed with intent and for safety for sure. And you can see that in the brochure.
Thank you. Which do you recommend? Direct duct connection to wood equipment or hoods over the working area?
Any type of source capture is going to be better. I mean, if you can, I would source capture with ducting than overhead hoods. Overhead hoods work well in welding when the weld fume rises because the thermal rise of it, wood dust settles out. So it's going to try to fall out prior to getting into the hood. And you may require a lot of CFM to create enough velocity, depending how far the hood is away from the process, to get it into the hood itself. So I would try to source capture it if all possible.
All right, so last question. How exactly are you controlling the VFD? I think someone's looking for more information on exactly how a VFD works.
Well, like I explained, there is an option for our VFD airflow controller that Donaldson offers, which monitors the static pressure at the fan and increases and decreases the static pressure, which increases and decreases the RPMs of the motor to maintain a constant pressure there. That pressure is a airflow because it equates over to airflow if you do this, the Q, Q equals VA, CFM equals velocity times area. There's a certain pressure in that ductwork at 5,000 CFM. That's where you're trying to maintain it. As the pressure drop goes up, of course, the airflow goes down, that pressure goes down, so the VFD ramp up to that pressure again to maintain that 5,000 CFM. So, and again, any of your TMs can explain that to you. Otherwise, some people put a pressure sensor in the ductwork somewhere in their system to maintain a certain velocity pressure in that ductwork based off what the VFD does. So you don't have to use our airflow controller. You can put something in the ductwork itself and feed that back to the VFD to ramp up and ramp down based off of what that static pressure is or what that pressure rating is.
Okay, there was one more question quick. So about duct losses, and I know we didn't really get into that. So I will say that we have a separate webinar for the person asking this that really gets into, it's focused on ducts. You can find that on our on-demand webinar page. And I'll shoot you an email with the link. But can you just briefly, you guys, explain how that is calculated, how you figure out the losses, the duct losses and determining static pressure?
Well, and that comes from any application, any system that you put out there. I mean, the industrial ventilation guidelines, which is what we're working on. I've been to the vent conference twice. It's a great tool to learn how to do the calculations. Each one of your capture points has a certain velocity pressure loss at it. Each linear foot of ductwork has a certain velocity pressure loss to it. Each branch entry, each elbow, all those things, all the explosion isolation devices, all the spark coolers, anything that's in that ductwork, a HEPA filter, anything that's in that system between the discharging back in the atmosphere and where they're collecting it off the process adds to that static pressure, the total static pressure of the system. So you have to, and I've done this to large systems, small systems where, you get a drawing of that. You have so much ductwork that's 8-inch that branches into a 10-inch with a 5 coming in the side. You can figure the friction losses on each of the components, the lengths of the ductwork calculated out. That's friction loss per much per foot. that gives you the total static pressure that you're adding up in the whole equation. So on that, again, that class that Amy mentioned there gets into that typically and more critical and lets you learn about it firsthand. It's industrial ventilation guidelines is what it is.
And that is our last question. So thanks to everyone for joining us today. We appreciate it. Great questions, really good Q&A session. Thanks for all the information, Chris and Dave, and hope everyone has a great rest of your day. If you have any questions, reach
Hey,
out.
Amy, one last point. So now we're going to be in Chicago in a couple weeks doing the industrial training. If you want to meet us firsthand, come on down and say hi. All right, Chris?
That's right. I
Absolutely.
forgot both you guys are going to that one. Yeah. So we have Chicago coming
Yeah.
the end of April.
Yep,
So if
and
that's
we're down
in
Chicago.
your area, reach out and we'll get you more information about it. Thanks, everybody. Have a great rest of your day.